So it's been a bit of a slow build to this moment. This is what this week's lesson is all about. And in fact, this idea right here is going to be what we build on for the rest of the term. This is the idea that's going to get tweaked and adjusted and manipulated, but repeated over and over and over again. Okay? So here we go. Let's get into it. We are trying to solve a circuit which has a resistor and an inductor connected in series. Okay? So there are 2 points that we should list, and they are going to be the rules upon which we will make the rest of our decisions. And it's these 2 points that you want to define each and every week for each and every circuit that we're going to do our calculations for. Okay? So the first rule is what we already know about series circuits. Okay, what is it in a series circuit that is constant? No matter where you take the measurement, no matter where you look in the circuit, what is the thing that is always the same? Series circuit, from start to finish, the current is constant. Okay, that means when we draw our vectors, we are going to use the current as the reference point from which we will draw all of our other vectors. Okay, because it's constant. That's the anchor that we can hang on to. Okay? The other thing, so that the first notion is about what kind of circuit is it? How are our electrical loads connected? In this case, they're series, which means the current is constant. The second point that we want to focus on is what kind of loads do we have in our circuit? And so what is our current to voltage relationship? Okay? So this goes back to the first video this week, where we talked about the fact that, I should mention this, series RL. So R is for a resistor, there it is, and L is for an inductor. So there it is. So what is it about the inductor that we just learned when we talk about the relationship between current and voltage? Okay, in an inductive circuit, in a circuit where we have an inductor, we have learned that the current leads or lags the voltage. Current lags by 90 degrees. Now we know that this is true only right here. All right, that's not going to be true for the entire circuit. We've got a resistor here as well. But specifically within this inductor, we know that that relationship is going to be 90 degrees. And so there is a right angle triangle that we can work from. Okay? So now, what we're going to do is we're going to draw some vectors, plot some vectors, and create 90 degree angles and right angle triangles that we can solve for. Okay? So let's start with this. Okay? Current is constant, so that's going to be our reference point. So let's put a current vector at 0 degrees. So let's draw a current vector right there. And we're going to use that for our conversations. Okay? And what I want to look at now, let's try and figure out the voltages in this circuit. Okay? Because when you connect loads in series, you have different voltage drops in the different locations in the circuit, right? So we can, and again, remember I mentioned in one video, this is the internal resistance of this coil. Sorry, this is the internal resistance of this coil. So this is all intertwined, but we're going to pull it apart. Okay, a bit of a thought experiment here. We're going to look at each part of the circuit independently, individually, so that we can do the math. Okay, so first of all, let's talk about, this is our current, right? That's a current vector. Okay, let's do a comparison and figure out what's going on with the voltage. Okay, so the first thing we're going to do is let's draw a voltage vector that represents the voltage that's being dropped across the resistor. And what's going to be the phase relationship between the voltage vector and the current vector? So if the current vector has been drawn at 0 degrees, and we could draw this anywhere, we're just It's so much easier to start at the beginning. Okay, so if the current vector is drawn at 0 degrees, where is the voltage vector going to be drawn at, representing the voltage at the resistor? Okay, well I drew that current sine wave within the voltage sine wave and said they're in phase if it's just a resistor. So I'm going to draw a voltage vector also at 0 degrees, okay, and I'm going to call this ER. Okay, so ER is the voltage dropped across the resistor. Okay, next I want to draw a vector which represents the voltage dropped across the coil. So at the coil, at the inductor, current lags the voltage by 90 degrees. So if the current vector is at 0 degrees, where's the voltage vector going to be? It's going to be leading the current by 90 degrees, which means I'm going to draw it at 90 degrees. So I'm going to draw it here initially. Actually, I'm going to do that. Yeah, for now, let's do this. Okay, and we're going to call this EL. Okay, so that vector represents the voltage dropped across the inductor. Okay, I hesitated here because I do want to change this. I need to change this, and I think I want to do it right now. Okay, because those are the two voltages dropped across our two loads. What we're really curious here about, what we want to solve for, is the total voltage in our circuit. So how do we take these two voltages that are drawn in vectors and use them to find our total voltage? Well, something we did last week. There's a reason we did all that stuff last week. This is going to be vector addition. Well, when we add two vectors together, how do we place them? We place them tip to tail. So here's where I hesitated, because I don't really want that vector there at all. Okay, here's the vector representing the voltage dropped across the resistor. I'm going to take the voltage dropped across the inductor, and I'm going to bring out here so that those vectors are placed tip to tail. So this is E subscript L. Okay, and now we need to add them together. And so this is the applied voltage. Okay, and this isn't really difficult vector addition like we were doing last week because we have a right angle triangle. Okay, so, and in terms of the right angle triangle, we need an angle theta. Okay, that's this angle right here, angle theta. This represents the phase shift in our circuit. Okay, that angle theta tells us the degree to which the current lags the voltage. Okay, we know it's not by 90 degrees because that would be in a purely inductive circuit, which is a hypothetical circuit, doesn't really exist. Every circuit has some inductance and some resistance. And so this angle is going to be something between 0 and 90 degrees, and we're going to be able to calculate for that. And that is what we call the phase shift. That is the extent to which the current lags the voltage in this RL circuit. Okay, so this is how we're going to do our calculations. Now, this is one triangle. Every time we solve a circuit, we're actually going to have three. Okay, so let's draw our second one. That's our voltage triangle. Let's back up and find our impedance values. So there's that new word again. And impedance is a fancy word for resistance. It's all of our resistances combined together. So let's figure this out. First of all, in terms of a phase direction, okay, so the vectors we have are for current and voltage. Okay, we can draw vectors for other things. They're not quite as literal, okay? But if we were to consider the direction, the phase angle that this resistor applies its force on the circuit, okay? So we've got the current at 0 degrees. We know that the voltage dropped across that resistor is going to be in phase. It's also going to be at 0 degrees. So there's no phase shifting here happening whatsoever. And so the resistance of the resistor also acts in the same linear fashion. And so we can draw a vector, again at 0 degrees, which represents the resistance of our circuit. Okay? The reactance in our circuit, okay, works at this theoretical 90-degree phase shift angle. Okay? So we talked about the voltage vector. We drew the voltage vector at 90 degrees to our current vector, which is our reference. We've left this here because we're always referring everything back to here. Okay, so if the voltage leads the current by 90 degrees, so we found the voltage vector at 90 degrees, then the reactance of that inductor behaves or influences the circuit in that, on that plane, okay, linearly in that direction. And so, again at 90 degrees, we draw XL, okay? And so what is the total impedance of this circuit with this resistor and this inductor, this inductive reactance? Once again, the hypotenuse is Z. I don't think I've offered you that letter before. Z is the letter that we use to represent impedance. Okay? And I could see the triangle that I erased as I was drawing the new one, and so I put it in the very same place to keep it to scale, because once again the angle theta is going to be exactly the same. Okay? Because these are just different variables within the very same circuit, and so the angle theta is going to be the same. Okay? Exactly the same. So I want to move on to the third triangle, and I'm not even going to completely erase this, because one more time, it is the same triangle. Okay? It's representing the same circuit, still the same angle theta, but what variables do we have left? Okay, this is a big deal right here, guys. Ho, check this out. We want to talk about power. Finally, I get to answer the question for you. When we were looking at transformers, we talked about the fact that we size transformers based on their VA. Well, what is VA? Well, VA is volts times amps. Well, isn't that watts? Well, yes, it is. What the hell is the difference? We are about to find out. Okay? Watch this. When we take our current and we multiply it by the voltage drop across the resistor, okay, these are in phase, volts times amps gives us a value for power. Okay? And this is what we call TP, which stands for true power. And true power is expressed using the units watts. Okay, so in a DC circuit where the only load that we have is a resistive load, we multiply by the voltage drop across the resistor, by the current through the resistor, and we get an answer in watts. Okay, we don't bother to call it true power, it's just power. It's the only power we have in a DC circuit, but it is this power using the units watts. Okay? Up here in the hypotenuse, which represents the total circuit, okay, this is what we call AP. And AP stands for apparent power. Okay, and apparent power is expressed using the units volt amps. Okay, so this is the difference. Here it is. The difference between watts and volt amps. They are different sides of the triangle. Watts is simply the work being done by the resistor. Volt amps is the total power calculated in the entire circuit. And this is why we must size our transformer in volt amps and not watts, because the transformer is the power supply. It must provide power for the entire circuit. It would not be big enough if it was sized to provide power for just part of the circuit. Okay? Which leaves us with this part of the circuit over here. And this is kind of a weird one. Okay? This is what we call RP, which stands for reactive power. Okay? And reactive power uses the units VARs. And VARs stands for volts, amps, reactive. Okay, VARs, volt, amps, reactive. Now, the reason this is kind of weird is because it doesn't really do anything in the circuit. Okay, true power is true power for a reason. This is where work actually gets done in the circuit. Okay, we generate heat, we generate light, we generate torque, whatever the case may be, work actually gets done. Okay, reactive power is stored energy. Okay, remember that was one of the things we said about an inductor, is what it does is it stores energy in the form of a magnetic field. And that's what this reactive power is. Okay, so one of the things I often say to try and keep this straight is true power is the power that you actually use. Apparent power is what you get a bill for at the end of the month. Okay, this is the demand on the system. This is what Ontario Hydro sends you a bill for. This is the power that you pay for. But this is the amount of power that actually got used. This is kind of wasted. It's stored. It's not valuable. It's not productive power. Okay? There's our different powers. All right? So I'm going to create one more video where I'm actually going to put some real numbers in here. Okay? But that's the process. We've got to build a triangle to understand the circuit, and then we can just move into using sine, cosine, tan, and Pythagoras to actually solve for different sides of the right angle triangle. Okay? So I'm going to leave this video here, come back and start fresh with a new video and put numbers on this.